So let's get started. First of all, you hear me all right? Right? Okay, good. So the plan today is to finish up the discussion on the quantitative treatment of the spin-orbit interaction first. And then we will see that the order of magnitude comes out to be very small. And then a characteristic constant comes out, which is the fine structure constant. After all, this spin-orbit interaction will give us what we call the fine structure in the hydrogen atom spectrum and other atoms as well. To be fair, we have to add back other relativistic effects of the same order, and then we will get an answer that is as good as any quantum mechanical treatment can give you for hydrogen atom energy levels. We will compare with experimental, highly accurate data, as I showed you in the first lecture in the atomic physics module. Then we will move on to another topic. We will revisit the Zeeman effect. And the Zeeman effect has to do with an external field. So we will have the situation that we have an internal field that is unavoidable, and then an external field depending on how big our magnet is. So we have competing terms, and in that situation, we have to decide whether the external field is bigger than the internal field or the other way around. That will lead us to different ways of handling the terms. So we will do the more important term first, naturally. And then we will go on, if time permits, then we will move on to a discussion of the hyperfine structure, which has to do with the nuclear spins effect. That is a tiny, tiny effect, even smaller than the fine structure. That is why it is called the hyperfine structure. But it's important for several reasons. First, nowadays, the SI unit of 1 second is defined by a hyperfine structure. Secondly, that opens up what in astronomy called the 21 centimeter radial astronomy. So that is the whole picture of our discussion based on the hydrogen atom. So this is our plan. Let's get back to our discussion on the spin-orbit interaction. We discussed qualitatively the effect of the spin-orbit effect. So let me recap the qualitative effect. The whole point is that we derived a form for the spin-orbit interaction. It goes like S dot L, that's why it's called spin-orbit interaction. But there's a prefactor, which is a complicated stuff, but it has to do with the landscape, the potential energy landscape of the field sensed by the electron due to the nucleus. So it's a Coulomb field. It has to do with the gradient of that potential energy profile. But this S dot L can be easily treated if we know the total angular momentum. After we defined that, S dot L can be obtained by J squared. Thereby, S dot L can be easily treated in the basis with J, Mj, and L and S. With this, if we first change basis to the description of JMJ, as we discussed last week, then this term can be easily handled with a lot of constants in front. But all in all, well, J is something like 1, 1.5, 2, 2.5, L is like 0, 1, 2. So all this stuff is order 1. So you have a constant of order 1. Okay, so 2.5 is order 1. So the whole thing is that you have an order 1 h bar square, and then there's an expectation value to do. But the whole point is that if an L, P state, L equals 1 add to a spin half, we will have 2 values of J. And this splitting due to J will have different splitting for different values of J. Thereby, the degeneracy behind all the P state, 6 of them, now is partially removed. For J equals 3/2, it will be 1 value. For J equals 1/2, it will be another value. So it is depicted here for the P state. Okay, so the degeneracy is not completely removed, but at least partially removed. This is the origin of having the fine structure. Imagine you have a spectral line doing this. You have another spectral line that, without this effect, there will be 1 line only. With this effect, there will be 2 slightly different wavelength lines. That is called the fine structure. Now, this picture is drawn not to scale, just to exaggerate the effect. So this is the fine structure. The actual thing is like 10 to the -4 eV splitting. We know that it is due to the smallest of the Bohr magneton that basically govern how big this magnetic dipole moment is in an atom. In comparison, the original line is like a few eV. From n equals 2 to n equals 1 is about 10 eV. So it is 10 to the -4 eV out of 10 eV. So it's 0.00001 effect if you take the ratio. Nonetheless, spectroscopy is a highly accurate experimental method. Thereby, the method can resolve such a fine structure. You have seen that in your lab course. There's one lab, you have a sodium lamp. And then even by your eyes, because that fall into the yellow range, your detector is good enough. So your eyes can see a doublet, 2 lines very nearby, and that is due to the spin-orbit interaction in sodium. In this week's sample question, the TA will estimate how big this internal field. There's no external field. That internal field is based on these numbers. So you have this splitting, one can estimate how big the internal field is. It is the same physics, although it's not hydrogen. In sodium, we have 1 electron in the so-called 3s outermost shell. So it can be excited to a p state. Due to spin-orbit interaction, the p state has J equals half, J equals 3/2. They take on slightly different energy. Therefore, the 2 transitions will be very close in wavelength, but different by a little bit, so much so that for the yellowish color, it is seen as a doublet. This is called the famous sodium doublet line. I think you have used it in one of your labs. So this is the take-home message. When we have spin-orbit interaction, we derive it. Once we have this term, we should use J to describe it. The reason is that once you use this, you can handle this term easily. Okay, so technically, by switching to this basis, we can form a diagonal part in the matrix formulation in handling the spin-orbit interaction term. So we are somewhere here last time. So next, we would like to repeat the discussion, but doing it in a more quantitative manner. We can only do that for hydrogen atom for the reason that we know the wave function of the unperturbed hydrogen atom, the whole set of functions that you solved it last term. So we can take those known functions and do the integral for the expectation value for the prefactor. Okay, and we know the form of the V of R, that is the Coulomb potential energy due to the nucleus. So everything is known, thereby we can really do something quantitative. Now for other atoms, spin-orbit interaction effect is there. The calculations will be very much more difficult because even the atom problem is hard to solve because we have many electrons in one atom. Okay, so think about palladium, say. Okay, so you have many electrons, and that is a difficult problem by itself. Thereby, it's not easy to do it in a quantitative way. So let's move on for this unique atom that we can do something quantitative. So we go back to our full form of the spin-orbit interaction term. We know how to do that by J. After we do that, we can easily use the basis of JMJ to handle this part. As discussed, this will give us an extra constant of order 1. In hydrogen, we have the luxury that we can do this particular expectation value. This is first order perturbation theory. Expectation value of using this basis of the perturbation term in between. All right. Now the angular part, the angular momentum part has already been taken care of, and this has to do with the radial R variable. Recall, in this wave function, here, all right? So in this wave function, there is a radial part of the hydrogen atom wave function. So this expectation value explicitly has to do with such an integral. We need to do an expectation value of 1 over R cubed with respect to hydrogen unperturbed states. Luckily, this can be done. Earlier in this chapter, I show you this table. I copy it through here just for your easy reference. You don't need to flip back, all right? So in particular, this formula is exactly what we needed for this 1 over R cubed expectation value. For exam purpose, don't memorize it. It is not to be memorized. It is to be derived for fun, all right? So we take that, and then this is the formula we copy from the table. That gives us an extra term, 1 over this thing. Okay, so I just copy the result and then rearrange the term a little bit. We have a chunk of constant, E square. We have 2 times 4 pi epsilon 0. Do you see that? And then we have some length more than square. But when we divide by length square, we get an energy, first of all. All right? So all in all, you will see the following. This shift can be rewritten as the following meaningful form. Let me make it clear. You are not expected to know how to derive this. If you want to know, try it out. Good for you. However, this result is important for cultural purposes. So let us analyze this result. After we got all this expression out, we rearrange the term to make the result physically meaningful. First of all, we can factorize out a zeroth order energy. That's fine, because this is an energy, there must be an energy there. Okay, so this is the zeroth order thing. It is explicitly this hydrogen state, hydrogen energy. Then there's a ratio. This ratio is the zeroth order energy of the nth state divided by the rest mass of an electron. Now, first of all, when you see this, this already indicates what we are considering. The spin-orbit interaction is a relativistic effect. We will have more to say about this factor. This is a very famous factor. Then the rest is just a number. It should be. Now, it's an energy shift. This is energy already take care of the unit. Ratio, no unit. Numbers, no unit. So everything is okay. This is at most something of order 1. That's not the focus. You plug in n equals 2, n equals 3, j is 3/2, 5/2. So what? You put all the things in, it is within the number of 1 to 5, around that number. Okay, so order 1, not our focus. The focus is this ratio. That is the zeroth order energy, this one, divided by mc squared. Okay, now what is the zeroth order energy? It's minus 13.6 divided by n squared eV, you know that. But this 13.6 means a chunk of constants. If we put this thing into here and work all the numbers out, this turns out to be of the order of 10 to the minus 5. It is a very meaningful number, as we will see. Okay, so next page, I show you what it is. So this is the ratio that we are interested in. The ballpark number is 10 to the minus 5. 1 over mc squared, nothing to do. 0 over the minus 13.6 divided by n squared is this thing. Apart from an n squared, everything is a constant. Okay, and then you simplify this at the end. It is this ratio square divided by n squared, well, times 2. All right. Now, this is the interesting thing. This is dimensionless. It has the number of 1 over 137. It is a combination of all fundamental constants. Charge of electron, h bar, c, the permittivity of vacuum, epsilon 0. Okay, now this combination is called the fine structure constant. The number is universal, right? So all the fundamental constants, it is worth remembering, it is 1 over, well, about 1 over 137. And even if we do first order perturbation for the spin orbit interaction, the shift is unperturbed energy times alpha square, not alpha, alpha square. So it is 1 over 137 is something like 1%, even smaller, okay? 1% is a good thing to remember. So it is 1% times 1%. So it's 1 over 10,000. 萬分之一啦, okay? So it is that small an effect. So let's put everything together. The shift will be 10 to the minus 5 times the unperturbed energy divided by 2n squared. Now, this fine structure constant, as we saw here, comes out from the ratio of the unperturbed energy and the rest mass energy. Another situation where it comes out is to think about the Bohr orbit, the ground state first orbit. What is the velocity of that orbit divided by the speed of light? Again, that signifies how important relativistic effect is in the hydrogen atom. And it turns out this ratio, you work it out, is again this alpha. So this alpha plays an important role in the development of physics. A cultural remark here, of course, optional, but cultural means for among physics students, this is something that you should know, okay? You don't need to know how to manipulate, but as the one member of the whole physics area, that is something good to know. Now, this alpha, fine structure constant, tells us something rather profound. You have charge square. It means that a charge is interacting with another charge, thereby you have charge square. So it is signaling, it has to do with something related to the interaction between electrical charges. Then there is something relativistic about it, C. And then there is something quantum about it, because there's an H bar. And it turns out, when we try a quantum field theory for the interaction between electrons in the way of thinking in terms of exchanging photons, that is how Coulomb field becomes quantized, then this alpha comes out naturally. So in so-called quantum electrodynamics, which is the field theory that has to do with a quantized non-interacting EM field, the result is that there are photons. And then we have relativistic quantum mechanics equation. We quantize the so-called Dirac field, which is the electron part. And then we let them interact. And that is the theory, what we call QED. In this theory, alpha comes out naturally. And we can do perturbation because of it is smallest. It is 1/137. We can do perturbation of increasing orders of these small numbers. It is called the small parameter in the theory. Because of alpha is small, QED is a very good theory in terms of doing perturbation. It converges nicely. Therefore, we can get highly accurate results. For example, the G factor, 2.0 something to 19 digits, we can calculate that thing out and compare with experimental measurements. The last statement I would like to make is that in some other quantum field theory, for strong interaction, for example, called QCD, we are not that fortunate. We don't have a natural small parameter like alpha, and thereby, even up to now, these QCD calculations are very difficult to do. You don't have a naturally emerging small parameter for you to do order by order perturbation. So that's much for the cultural remark. Let's get back to business. For this result, notice once again, it depends on n. So which level you are thinking about, n equals 1, n equals 2, and then the L, S state, P state, and J. We can take this and we write it in terms of n and L. By separating the case where J is L plus half, we can plug J equals L plus half into that expression and then come out with this. Another possibility is J equals L minus half. You will get that. Okay, so this is equivalent to our previous result, but written in two different ways. You may wonder why I want to mention this. Stay tuned. So if we are only interested in spin-orbit interaction, then we are done with the whole discussion. This is the result. This one, done. But we discovered that our results is of the order alpha square. If you attend the exercise classes in week 3, right? The TA did an example for you for the perturbation results of relativistic correction to the kinetic energy term. In that calculation, first order perturbation also give you a shift of the order alpha square. Therefore, for hydrogen atom, to be fair, we should not stop here. Therefore, I will continue to complete the discussion on hydrogen, but not spin-orbit interaction. We are done with spin-orbit interaction. But to be fair, we have other effects of the order alpha square that we should put together in the hydrogen atom case. Now, for other atoms, we don't need to do that. In our discussion of the spin-orbit interaction Hamiltonian, there is a dV/dr term. Usually, for bigger atoms, heavier atoms, that term will be bigger and bigger. Thereby, that term will dominate over the relativistic correction to the kinetic energy term for heavier atoms. For hydrogen atom, unfortunately, there is comparable terms that we need to put together. So the nice thing of hydrogen is that we can do something analytic. The bad thing of hydrogen is that we are not done yet. If we stay in this order, there are similar magnitude terms. So this is a result that I copied from the sample questions. We have done this in the exercise classes. In the kinetic energy expression, if we start with the relativistic expression and subtract off the rest energy, that will be the kinetic energy. The first order term will be this as the perturbation. TA did that. I copied the result. It is a shift first order with respect to the unperturbed energy order alpha square. Now, same thing. And then factor of order 1. So to be fair, we should include this and then see what is the shift due to two effects, two relativistic effects. So we put all the things together. This is the result, the box. If you want to work it out by yourself by putting this term together, you better use this form. This is why I put it here, okay? For the spin-orbit interaction, and then you put it together with this. After one page of work, you will find this box. So let's focus the discussion on this box. Now, this is a very famous result. For one reason first, Dirac has his own Dirac equation. This is relativistic quantum mechanics equation. He solved it for the hydrogen atom, and he got this expression, equation 40. So we have two ways to get at this thing. That is why, first of all, this is a very famous result. Now, let's analyze this result. We have a unperturbed term. This is the Bohr model or the Schrödinger result for a hydrogen atom. There's a bracket, so this one is the zero for the thing. You did it in last term. Then in our context or in our toolbox, we don't have Dirac equation. That is beyond our course, relativistic quantum mechanics. But we consider term by term, spin orbit, relativistic correction. Then we come out with this correction term that is related to alpha square order. Okay, so this is 1% times 1%, tiny, first of all. And the result depends on N and J. Now, of course, you can write back L because J and L are related. J is L plus half, J is L minus half. Okay, you can put together the final result. So all in all, at the end, the energy level split according to N and J. So let's see what is the implication. Let's look at this side. This is the physics, okay? Don't worry about the mathematics. Last term, what you solve at this level, N equals 1, I mean this line, you see that, okay? N equals 1 minus 13.6, minus 13.6 divided by 4, minus 13.6 divided by 9, divided by 16. So these are the unperturbed results. Now, N equals 1, J equals half is the 1s. You calculate this thing out, it is moved down a little bit. But this is highly exaggerated so that you can see it, all right? Now, so you have this. Let's look at the 2p. 2p, last term, it is this minus 13.6 divided by 4. Do you see that? Okay. But now, 2p means N equals 2. And then you have two J values. J could be 1 minus half, which is half. 1 plus half, which is 3 over 2, 1.5. You plug that in, you get two numbers. These are the two numbers. Okay, so 1 belongs to J equals half. The higher one here belongs to J equals 3/2. Okay, do you understand what is being plotted? Understand? Try to draw out the answer of including all this relativistic effect into hydrogen. All right. Now you can move on to N equals 3. Use the formula. You can make your own plot. Okay. So here for N equals 3, you have the P states again split into two J values. The D states. D state. L is 2. Okay, L is 2 means J is 5 over 2 and J is 3 over 2. Plug numbers into them, you will get this splitting. Here. Okay, this is the 3D. All right, now let's compare this thing. This is interesting. For the P state, 3p, it will give a J equals 3/2. For the d state, there is also a j equals 3/2. Okay? And according to this formula, same n, same j, they are the same energy. Okay? I mean this one. Same j, same n. Similarly, n equals 2. This is j equals 1/2. From the s, this is j equals 1/2, but it comes from the p. According to this formula 40, they are the same energy. Okay, so this is as what the formula from Dirac equation on one hand, or from our perturbation toolbox, taking into all relativistic effect, that is what we got. So it will be interesting to compare with real data. Does it work? Now we have a theory, we are doing applied quantum mechanics, we compare with data, all right? So take this point in mind, same n, same j, according to this formula number 40, they have the same energy. We will see whether it works or not. It really depends on your taste. My answer is yes, 99.99%. So we better compare with spectroscopic data to see whether it is true. So we have the result. We want to compare with data now. But when you compare with data, you are talking to experimentalists. Physics is an experimental science. Therefore, we need to train ourselves to talk to experimentalists. So that's why I have these few pages here to introduce what is called the term symbol. You may say this is not physics. I would agree with that, but this is a way, as a shorthand notation, to pack a lot of information into one symbol about the quantum numbers in the angular momentum. So let's see what it does. It is a notation to label the energy levels. In hydrogen atom, we have been using L, S, and J, but this S is 1 electron for hydrogen is always half. Okay? But what we are talking about works also for other atoms. But in other atoms, we usually use the capital letter. L would mean the sum of the electron's orbital angular momentum. Big S means sum over the electron's spin angular momentum, and J is L plus S, the capital ones. Just very similar, but usually the capital letter symbol works for all the other atoms, and we have been using the lowercase for hydrogen atom. The labeling meaning remains the same yet, still, right? Okay, so what is the term symbol? The term symbol is here for hydrogen, okay? So focus on the highlighted box down there. It is a compact notation with all this information about the orbital angular momentum number L and J and spin all packed into a simple compact form. The L lies in the middle, but we don't use a number to represent it. So P state, we will not write a 1. We will write a P. Okay? So there's a dictionary here. When L is 0, we call it S. When 1, we call it P. 2, call it D. 3, call it F. And then run out of letter 4, call it G, and so on. Historically, this has meaning from spectrum. That means there's a sharp line. So S, okay, and then I think this is a principal line, and this is a diffuse line, not so clear, and so on. Then they run out of symbol, then start to call it F, G, H, I, J, K. All right. So, but that is just a dictionary. So we will put such a notation in the middle, and spin. We don't put S. Instead, we put the degeneracy, 2S plus 1, the multiplet number on the left, this is left-hand side upper corner. And then we have the total quantum number J in the right-hand lower corner, okay? So in one notation here, we have all the information, L, J, and the spin, but hidden. You have to reinterpret, or when you see that is 2, what does it mean? It is half, S is half, because 2 times half plus 1 is 2, okay? So when you have other atoms, you will see the capital thing here, the capital J here, the capital 2S plus 1 there, same thing. So let's see how it works. Hydrogen ground state. It's a L equals 0 S state. So we put a S. Because it is L equals 0, spin is half, J can be half only. So we put a half down here. We have only 1 electron, spin half, 2S plus 1 is 2. So, summary, this is hydrogen ground state. Okay? As in some handbook or table, to be very clear, there's a prefactor 1S, that is the 1S level, because you would have 2S as well, sometimes in other atoms. So 1S and then this term symbol. Okay? Excited state, how about that? You excited to a 2p state. So P is L equals 1. So put a P in the middle. But according to total angular momentum, J can take on 2 values, 3/2 and half. Therefore, there are 2 possibilities of slightly different energy, spin-orbit interaction. All right? And then 1 electron only, spin half. Okay? So you have 2 term symbols for the P states. Then the question is, which one has a lower energy? Then we need to work out the spin-orbit interaction effect. Our result shows that this is slightly lower. Okay? Therefore, we have the language to talk to experimentalists. So when you see data, it will show you this thing with some numbers. Now we are prepared. So this is just a remark. For general atoms, we have to add up orbital to a capital L, add up spins to a capital spin, but the term symbol remain the same structure. This is the orbital, this is the total, this is the spin, but in the form of 2s plus 1. Now you can talk to experimentalists. We started off the module by looking at this table. Now, by the end of this very long discussion on this perturbation treatment of spin orbit relativistic effect, we go back to the same data table. I hope now you feel more comfortable about this table. Now, you have this 1s. The term value is a s, L equals 0. The j is half. It should be put here, all right? And then 2s plus 1 is 2. So s is half, 1 electron. This is the ground state. It is set as 0. Now, the interesting thing is you have 2p. There are two values of j. There are two different numbers. Still not fine, because according to our result, n and j will determine the energy. Different j, different energy. We are doing okay. First order perturbation only. We have made a big jump in our knowledge, you see. Now, something interesting here, 2s. J is half again. Our result says this is n equals to j equals half. This is n equals to j equals half. We expect this and that to have the same energy. Well, it's pretty good. 82258.9. Rather impressive, you see? It's like 10, nearly 100,000 and off by 0.01. 1 part in million, something like that. Huh? So our theory is really good, okay? But be an optimistic person. Well, for those who are pessimistic, you may say, they are different. Good, they are different. And that is a mystery. Our result is as good as any relativistic quantum mechanical calculation can give, all right? Now, similarly, we will see the same thing. Our theory predicts same n, same j should be the same, but there is a slight splitting in the real data. So here, this table intentionally drawn in the way that we introduce the term symbol, all right? So I mentioned that this and this, same j, same n. We expect it to be the same, but starting from this integer, slightly different. But I must say it's slightly different, okay? I would not exaggerate the difference. Now, let's go to n equals 3, and then j equals half. Our formula said they should be the same. Again, it's pretty good. It's really 1 part in a million, I think, right? But slightly different. It is 0.01 in 97492.2. You know, our quantum mechanics is quantitative, and we can do it by doing an integral. It's pretty nice. Now, n equals 4, okay? N equals 3, we have 2 3/2 situations, and then they are different by, now this is even crazy. Now, only off here, okay? And then for n equals 4, there's some difference. Again, tiny, it's already bigger out here, okay? So the percentage is getting smaller. And the same j, slightly different here. Wow, really impressive. And then same 2.5 here. I think maybe there's some difference in the next digit when more highly accurate experimental data comes in. So, conclusion is that we are almost there, but indeed, we saw slight differences when the same N and same J, they turns out to be slightly different in energy. Okay, so we have this, we have that. So we have this, we have that. I'm talking about this, all right? So let's go back to our figure. We just discussed that. What data says is the following. These two, from the formula at our level, they are the same. They are predicted to be the same. Experiment says, look closer, okay? For the treatment we have, they should be the same, but data says this one is this wave number, and this one is this wave number altered by this tiny bit. Okay, so I would like to conclude that our Schrödinger equation plus spin-orbit interaction plus relativistic correction plus perturbation only is already pretty good. It's 99.99%, I would say, maybe even 0.999%. Highly accurate already. So what is this tiny difference? This is called the Lamb shift in hydrogen literature. It has been a mystery. After we worked this thing out in the 1930 something, and then when experiments become more and more accurate, we started to see this difference. And the explanation of this shift is more advanced. As I hinted at, we need quantum electrodynamics. I have a big picture, okay? So here is a cultural thing. What is missing in our treatment? In our treatment, what is missing is that we are handling the proton attracting the electron in the hydrogen. And in between, there's nothing. Well, our picture is there's nothing. However, when we use quantum field theory to handle hydrogen atom, this nothing, there is something in this nothing. For example, this nothing called vacuum could occasionally comes out as an electron, anti-electron or positron pairs. And then they will annihilate themselves a little bit later. So this kind of popping up more particles and then annihilating themselves leads us to something called vacuum polarization. It means it has some effect on the net inference of the nucleus on the electron due to the popping up of particle-antiparticle pairs in between. This is not included, and this cannot be included in any quantum mechanics treatment. In quantum mechanics, when we have one particle, one electron to start with, we always have the same number, one electron during the whole calculation. There are no rooms left for varying number of particles. Only in quantum field theory, that is designed to handle varying number of particles, and therefore that can handle the vacuum in between. That nothing is something. And that effect leads us to the Lamb shift. Slightly shift here. Okay? So I think at this point, I would take a short break, and then we will move on and I will answer some of your questions.